review what we discussed yesterday. So what I'm trying to do is to review the concept of multi-resolution, the ability of representing the signal in a multi-resolution sense. Yeah. Over here, the signal is very, very far away. The tiny low pass. Over here, the signal is very, very far. And as you see, all the detail and structure of the signal. After this, we'll review the two-scale relation equation that deal with the scaling function and wavelet, and then we'll show how to solve those equations. Okay? So after that, we have a break, and then we have I will spend about an hour and a half on application of wavelet. And then after the break, from 11:50 to 12, I have some research topic that I'm working on. That I can discuss some of the topics that that's the plan. Okay, so we present an example yesterday regarding how to take a piecewise constant signal. Right? We have this particular signal right here, something like that. 1/8 unit interval, and then we see that we can take this signal and we can decompose it into a fourth approximation by taking averages of every two coefficients, right? And then we have a detailed signal. We add them together, we have the original signal. The interesting construction is from 1/8 piecewise constant signal. The post approximation will be 1/4, 1/2, and 1. Okay? And through this construction, we notice that the basis function of V0, say, is phi of t, and the basis function for W0 is W of t. And this is basically we're dealing with piecewise signal. So this is a straight line, 1, that will be phi of t. And then to capture the change, we capture it in W of t, which is 1 and minus 1. Okay? And we can see that if you combine these two together, you can construct a space. The basis function will be phi of 2t. And the detailed space will be the basis function W of 2t. And you can iterate on this process to W of 4t, W of 4t, and phi of 8t. Right? Now, if I do this kind of process, we said that I can write x of t, in terms of basis function only in V3. As I can say that x of t can be written in terms of summation. Okay, I can say a phi of 8t minus k, and this is ak, right? I'm going to say a 3k, okay? So you see this is V3. Right? So basically, phi of 8t is the basic function, and any signal in that piecewise constant to 1/8 interval will be a linear combination of this. K can go is a causal signal. It will from 0 to infinity, and K from 0 to 7. Your support is from 0 to 1, and so on. Okay, so that's how, using the basis function phi of 8t, I can represent any signal x of t with a 1/8 unit interval. Okay, that's using only space V3, right? This is only using V3. But I know that another way to do this is to represent using V2, W2. So the second line I'm going to write is using V2, W2. Okay? So the first summation, okay, we'll deal with phi of 4t minus k. That is the V2 space. Okay? The next one will be a summation of W of 4T minus K. This is the W2 space. Right? So I will call this A2K. A is the basically for approximation. Okay? And this is to be B2K. Right? Okay, in our example, what are the coefficients for B2K? Remember it's -1, -1, 0, 0. Right? That's in our example yesterday. Okay? And this is using B2 and W2. Well, how many other ways can I represent the same signal? 2 more ways, right? I can have V1, W1, and W2. Okay? So basically, we'll keep this the same. And we have V1 and W1 here. We have 3 summations where this one stays same. The V2 space stays same, right? So in V1 space, I have summation K, A1K, P of 2T minus K. That's the V1 space. Okay, and I have W1, which is summation K, V1K, W2T minus K, and then we'll just have this copy over. We have summation K, V2K, W4T. Okay. So this is V1, W1, and W2. Because V1, W1 will give me V2. Okay? And the next one is very, very simple, right? You can see that. And then V0, W0, V1, W2. So we decompose this into 2. Right? We have summation K, A0K, 3 of T minus K, that's V0. And then you have W0 with summation K, V0K, with T minus K, then I have divided 2. This is the one that we use V0, W0, V1, W1, W2. Right? So in general, you always have a coarse approximation space, right? You also have a V, the low pass representation at that one particular space. And then depending on what you want, where are you at the resolution, you have various details. Okay, so the most general way of writing this is, so the most general. What do you have? You have a space, right? You have summation in K, A0K, 3 of T minus K. And then you have a combination of this, okay? So I'm going to have a double summation in that, right? Let's go to the first one is J in K. J will go from 0, 1, and 2. Right? Now if I have, 1/16 is quite constant, then J from 1 from 0 to 3, and so on. Right? So this J is telling you, what are where are the detailed signal. Right? For this case, it goes from 0 to 2 because our signal except T is 1/8, right? 1/8 is 1 and 2/3. So 0, 1, 2. Okay? And then K, E, J, K, W, 2 to the J, T minus K. Right, so see, we have 1,